Hello students, and welcome to the video for 3.04 Valence Electrons and Bonding. As always, we want to first just mention the standards that we'll be covering in this particular lesson. You can find all the Common Core standards by going into your course, selecting course information, and then scrolling down to standards. For this particular lesson, our objectives are to define ionic and covalent bonding, and then relate what we've learned about periodic trends to chemical bonding. So let's go ahead and get right into it. Again, remember, you do need to have some prior knowledge before going into this lesson, so make sure you have lessons 3.01 through 3.03 completed, looking at the periodic table, how it's laid out, the different groups, different trends that we see throughout that, throughout the periodic table. And once you're feeling comfortable with those, then you can go ahead and proceed with 3.04. Alright, so for 3.04, first off, just some introductory stuff here. Generally speaking, neutral atoms are rarely found in nature. Okay, and the exception to that is noble gases. And the reason is because noble gases are unreactive, and that's because they have a filled outer shell, a filled valence shell. And that's what we're going to be looking at throughout the remaining sections here in Module 3, is how do other atoms get that filled outer shell? Well, the way they do that is they bond. So here we're going to be introducing this idea of bonding. Most atoms are found in compound form as a result of all this bonding going on. Basically, when we're talking about bonding, what we're looking at is the electrostatic attraction that holds the atoms together. That same electrostatic attraction also is attracting electrons from other atoms that are nearby. So when you have two nuclei having a mutual attraction for the same valence electrons, then what's formed is called a chemical bond. And of course we have two different types of chemical bonds that we're going to look at here in a moment. We classify them based on the way those electrons are distributed within the bond. And there's basically two things that can happen. So let's look at those two different scenarios. Alright, the first one we call an ionic bond. Alright, this is a chemical bond that results from electrostatic attraction between positive and negative ions. Now, the way that happens is atoms will gain or lose electrons to become charged particles. Generally speaking, what's happening is metals will lose electrons and the nonmetals will gain those electrons. And we'll talk a little bit in a moment here as to why, that's the direction it happens. So when the metals lose an electron, what's left behind is a positive ion. And then when the nonmetals gain electrons, they now become negative ions. And of course, we've all heard that, famous saying, opposites attract. So you have a positive ion, you have a negative ion. They're going to attract together and form a bond. And that's what we call an ionic bond. So to make that ionic bond, what's occurring is simply a transfer of electrons. And that's this last bullet point right here. We're transferring electrons from the metal to the nonmetal, thereby forming ions that are oppositely charged, and then they attract to one another. In a covalent bond, on the other hand, here the electrons are going to be shared. Instead of them actually transferring from one element to the other, they're simply going to be shared between the two elements. Okay, so there's no gaining or losing electrons. Generally speaking, this is only going to happen between nonmetals. And because they're sharing them, we can kind of say that both nuclei own those electrons. Okay, so again, in ionic bonds, electrons are being transferred from metals to nonmetals. In covalent bonds, they are just sharing those electrons. And just want to point out that when you're saying electrons here, we're talking about the valence electrons, the outer shell electrons. Alright, so we of course have two different bonds then. We need to kind of be able to compare them and determine what type of bonds we're going to have depending on the elements involved. Okay, so they do range in strength and properties between those two types. There's not a real distinct cutoff necessarily. And to do that, we're going to compare their electronegativity values. And if you remember back in 3.03, we talked a little bit about electronegativity. It is simply the attraction of an atom for electrons. So the greater the electronegativity value, the more that atom wants to attract or bring in more electrons than what it already has. And that number can then be used to determine if we're going to have an ionic bond or a covalent bond. Generally speaking, down here on the bottom, generally speaking, the greater the difference in electronegativity values, the more ionic the chemical bond is going to be. Okay? So basically we're going to take the two elements involved in the bond, we're going to look at their electronegativity values, and we're going to determine the difference. And of course, you know from math, the difference means we're just going to subtract those two numbers. The bigger that number, the more ionic it is. The smaller the number, the more covalent it is. Simple as that. Okay? So, a good way to kind of think of it is like a tug of war. Okay? If you imagine two people having a tug of war, and in the middle, instead of there being a flag like you typically would see in a tug of war contest, there's those electrons. And we're basically, determining who's going to win those electrons. Well, if you have one person that's really strong and another person that's not, of course we know that the stronger person is going to win. In that case, the electrons get pulled all the way over towards the stronger person. So this is an illustration for an ionic bond, where all the electrons get pulled, well not all, I shouldn't say that, the valence electrons get pulled over to the stronger one. Okay, so we have that transfer again that we talked about a moment ago. There's a transfer of electrons from one atom to the other. So when they have a large difference in electronegativity, the one with the greater electronegativity is the stronger person. Okay, the one with the smaller electronegativity is the weaker person. So again, the one with the stronger electronegativity is going to take that electron. And as a result, it's going to be the negative ion. And then, of course, the other one now, because it's lost its electron, is going to be the positive ion. And then the bond forms between them, making the ionic bond. All right, now another scenario we could have with our tug of war is, the illustration in the first bullet. If you have an older or younger sibling, and you try to share toys or video games or, the TV, whatever it might be, generally speaking, right, the stronger person is going to probably be sharing a little unequally, right? And the one person is going to have the TV more often than the other person, or is going to have the toy or the video game more frequently. So there is sharing going on, right? They both are having the opportunity to use the television, as an example, but one is definitely using it more than the other. Okay, this is an example of uneven sharing. There is sharing, but it's definitely not a fair or even situation. Well, when we're doing bonds, we call this type of bond a polar covalent bond. Okay, a polar covalent bond. Because electrons, the same thing happens with them. Sometimes we have one atom that's slightly stronger than the other one, but not strong enough to actually take the electrons away. So they're still sharing the electrons, but one atom has the electrons more frequently than the other atom does. And that's where we get a polar bond. And the reason it's polar, if you have done magnetism before in physics or physical science, polar simply means that you have a positive in and a negative in. So when you have an uneven sharing of the electrons, one atom is going to have the electrons the majority of the time, so it's going to have a slightly negative charge to it. The other atom is not going to have the electrons very often, so it's going to have a slightly positive charge. So if you look at the picture up here on the top, this is just an illustration showing what we were just talking about. We have two atoms. That's the dot right here. You got the dot on the left and the dot on the right. Those are our two atoms. Now the one on the right here, we drew a little bit bigger to represent that it has a larger electronegativity, so it has more attraction for the electrons. But it's not strong enough compared to the other atom to actually completely take the electrons. So you can see by the electron cloud picture here that the electron, the majority of the time, is over here by the one with the higher electronegativity. Every once in a while, though, it is going to be over here by the one with the least or smaller electronegativity. So you end up with the electron cloud kind of having this egg shape where it's unevenly distributed between the two. So this side of the bond is going to be the negative end because that's where the electrons are the majority of the time. This end is going to be positive because that's where the electrons are the least amount of time. And that is a polar bond. Alright, so again, the first scenario, one is extremely strong and takes the electrons away. In this one of them is stronger but not strong enough to take them, so they still share. They're just sharing unevenly. So the third scenario, probably no surprise, is when they share evenly. Okay? In this case, again, just kind of going with our tug-of-war illustration here, we have two people, same size, same strength, and they're both trying to pull, in this case it looks like a football there, from one another. There's going to be a standoff. So I'm sure you've all seen a tug-of-war before where the flag just sits there in the middle and nobody wins the battle, right? Well, it's the same type of thing over the electrons. You have two atoms that have equal electronegativity, so they have equal attraction for those electrons. They're going to pull on it with equal strength. Neither one of them is going to take the electrons from the other, and neither one of them is going to unequally or unevenly share them. So in this case, they are going to be equally shared, and that is called a nonpolar covalent bond. All right, and the reason for that is because they're equally shared, they're going to be equally distributed in the electron cloud. So if we were using our illustration from the last page there, right, if I had my two atoms and they have equal electronegativity values, then the electron cloud is going to be evenly distributed around both of them. So there's not going to be a positive end or a negative end. Right? So since there's no poles, it is not polar, so it's called a nonpolar covalent bond. Okay? So again, we've got an extreme case where we're taking the electrons, we have an uneven sharing of electrons, and then we have an even sharing of electrons. So again, remember we said it all goes back to the difference in electronegativity values. So here's just a little diagram. If the difference between the electronegativity values is between 0 and 0.3, then you have a nonpolar covalent bond. Okay? By having a small difference, that means their electronegativity values are basically the same, so they're going to equally share or evenly share those valence electrons. If it's between 0.3 and 1.7, then it's going to be polar covalent. Again, in this situation, they're still sharing, but one of them is strong enough to kind of take the electrons the majority of the time. So we end up with one end of the bond being slightly negative, the other end being slightly positive. And then if it's over 1.7, then it's going to be an ionic bond. In those situations, the differences are large enough that one of the higher electronegativity is just going to take the electrons away from the one with the lower electronegativity. Now this is something you're going to use in later lessons, but right now let's just go ahead and practice this real quick. Here is the periodic table with electronegativity values. And back in lesson 3.03, remember we mentioned that it's an arbitrary scale with fluorine being labeled as 4.0 because it has the highest electronegativity, and then everything else is compared to fluorine. So fluorine has the highest, 4.0, and down here at the other corner, francium has 0.7. And if you go back to 303 and we talked about periodic trends, that would make sense, right? Because as we're going down a group, electronegativity is getting smaller, and as we're going left to right across the table, electronegativity is going up. So now on the bottom we have two examples. Let's say we have sodium bonding with chlorine, and we need to know what type of bond that's going to be. Alright, so let's look up our values. Sodium is over here on the left side in A. That's sodium. And it has a value of 0.9. Okay, so we'll just write that down here. We got 0.9 is the electronegativity for sodium. Chlorine is over here on the right side of the table, Cl, and it has a value of 3.0. Okay, so we'll write that down here. 3.0. Now remember, we want the difference, so we're going to just subtract these two numbers. Now since we want the difference, it's kind of like absolute value, so you can switch it around and just say 3 minus 0.9. And of course that's going to give us 2.1 for the difference. So our 2.1, if we go back to our chart on the last page, that is greater than 1.7. So that tells us this is going to be an ionic bond. Now if you remember back in the very first slide when we talked about the definitions, we said ionic bonds happen between metals and nonmetals. So this does make sense to us because sodium is over here on the left side of the table, so it's a metal. Chlorine's on the right side, it's a nonmetal. Okay, so we got two things, two tests if you will, that are telling us that we have an ionic bond between sodium and chlorine. Alright, so the sodium, because it's a metal, will give up its electron to the chlorine. Or excuse me, will give up its valence electron to chlorine, and then chlorine will take it in. So you have a negative ion on the chlorine, you have a positive ion on the sodium, and then they attract to each other to make the bond. Alright, now for example 2, we have nitrogen, which is 3.0, bonding with hydrogen, 2.1. So let's write those down there. For nitrogen, again 3.0, hydrogen 2.1. Now notice that I wrote here the formula in the parentheses, NH3. Even though there's 3 hydrogens, we're not going to multiply the 2.1 times 3 because there's only one type of bond. Okay, I'm going to go up top here where I have a little room and draw this. Ammonia, NH3, we drew the Lewis structure, which we'll talk about those in a later lesson, but it would look like this. Okay, so we have an NH bond on the left, an NH bond on the bottom, and an NH bond on the right. It's still an NH bond, so we don't multiply it by 3 to figure out if the bond is electronegative, or excuse me, if it's ionic or covalent. We're looking at each bond individually when we do the difference. Okay, that's a common error that we do see folks making. So when we subtract these, we end up with 0.9 for the difference. Well, if we go back to our previous screen, we know that 0.9 falls between 0.3 and 1.7. Therefore, it will be a polar covalent bond. Okay, it's going to be right in this range somewhere. So that means all 3 of those bonds will be polar covalent. Okay, and that's all it is. We just take the 2 values, subtract them, and that will tell us what type of bond we have. Alright, so just kind of summarizing things here now. Again, in general, the nonmetals form covalent bonds with other nonmetals. and the metals will form ionic bonds with nonmetals. So over here on the right, you can see this little diagram. I have in the first one two atoms with a valence electron, and they share that electron. So now the atom on the left, you can follow his ring. You can see that he owns, if you will, both of those electrons. But then the atom on the right, if you follow his ring, they also go through those two electrons. So he also owns those electrons. So they are sharing. Whereas in the second illustration here, the electron on the left is transferred to the atom on the right. Now we have a positive ion on the left here. Right, we've got the positively charged nucleus with no electrons around it. And then over here we have the negative ion. We've only got one positive charge in the nucleus, but we have two negative charges in the valence shell. So that gives us a negative ion, and then there's a traction between them because they are oppositely charged. Alright, so going back to that question as to why bonding occurs, I briefly mentioned the octet rule that you'll talk about in a later lesson, but the reasoning behind that too is that it's all about the potential energy. Atoms, just like anything else in nature, prefer to be in their most stable situation. In other words, their lowest amount of potential energy. Well, generally speaking, atoms are going to have a lower potential energy when they are bonded to other atoms than when they are by themselves. All right, and that's our main reason for atoms making bonds in the first place. Alright, so that was a pretty quick and easy one. Make sure you go through the lesson tabs and do any examples and practice problems. If you still need some help, feel free to attend our open tutoring. And of course, we also have other resources in the Resource Center. And for this particular assignment, there is no official assessment that you will need to submit, but be sure you understand the material because you will be tested on this later in assignment 3.05. I hope this was a helpful video, and we look forward to seeing you again soon.